Hello everyone, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This one will be an interesting one because it's looking at the entire sky. So what we do sometimes in astronomy, and in fact it's not just taking individual pictures, sometimes what we want to do is we want to take an entire survey as much as possible of the entire sky. And that shows us what's in the sky, just like making a map of the Earth back when people were doing major exploration. Making a total map of the sky is also one of the most important explorations that we can do. So we see here a series of small images that show what the sky looks like in various wavelengths, and the information gathered by looking at all these various wavelengths actually tells us incredible amounts of information about the nature of the cosmos. So let's take a look at the first thing and remember that we're looking at the full sky. So this is called an ATOF projection, and it takes the surface of a sphere. The Earth is spherical, it's round. Oh my God, did I have to say that? It's round, and then what we do is we project it onto a two-dimensional surface. It is a round thing. There is no flat Earth. Anybody who says so is quite crazy. In any event, what we do is we think that the edges go linking up. One of the edges links up to the other edge, and you can imagine it being sliced at the far side and they actually projected around so that they actually are maneuvered around. So what we're looking at is we're going to be looking at a similar projection of the full sky. So if you go off the right-hand side, you come onto the left. If you go off the left, you come onto the right. But if you go to the top, you do not go to the bottom. So it's only a left-right cut. All right, so the first thing we'll look at is an amazing pastiche of pictures that was put together by Axel Mellinger, and this has been preserved at the NASA Goddard Spaceflight Center's Lambda data set, which is a place where they take all sorts of amazing images. So Dr. Mellinger took a huge number of ground-based observatory images and stitched them together for a full sky image. And you can kind of see that in this image that look kind of stitched together because it was made by numbers of different observatories. You can see that there's some slight color variations across it. But the most important thing that we see is that this is visible light, and it's a color visible light image. He tried to balance them out so they're the same rough color. Across the middle, now typically for all of these surveys that we're going to look at, we're going to look at them from the galactic plane. So going across the middle is the Milky Way, and directly in the center is the center of the Milky Way. So this is not according to the sky, according to fixed positions such as the equatorial coordinate system based on the Earth. No, this is a coordinate system based on the plane of the Milky Way, which is the most natural thing you see in our sky. So because it basically makes a line, so why not keep it that way? So we see that in the invisible light, we have some certain features. Directly in the center is the center of the Milky Way, which is a collection of billions upon billions of stars. And surrounding that are some dark patches, which is dust blocking the light. We also see some pink glows that tend to be more centered roughly on the plane of the Milky Way. That's hydrogen gas and star-forming regions. Down into the center lower right, we see two sort of bright patches. Those are the large and small Magellanic Clouds. And off to the left-hand side, about halfway out the side, almost 2/3 the way out from the center, on the left-hand side is a bright spot. That is the Andromeda Galaxy. So anyway, we see Orion off to the extreme right, but basically the major colors are stars, gas, which is the pink glow, and dust, which is the dark things that absorb light. Amongst that is also, above and below the plane will be galaxies and other stars that are close to us. So that's kind of our view of the sky in the optical view. Now we can look at specific wavelengths of light. One of the more important optical wavelengths of light is hydrogen alpha, or 6,563 angstroms, or 6563 nanometers, and 656.3 nanometers, I should say. And this is H alpha, which is the glow due to hot clouds of hydrogen gas. And we'll go back and forth between H alpha and the optical image, and you can see the patches where the H alpha is bright, and again it's centered on the center of the plane of the Milky Way. And H alpha glows because some very hot stars are in the presence of hydrogen gas. And so they ionize that gas, and as the gas recombines, it glows in specific wavelengths of light, and one of them is H alpha, and that is the pink glow associated with hydrogen. And we can see that H alpha map is very patchy, and that's because we're looking at patches of hot locations across the Milky Way. And the C-like structure on the extreme right in this image, that's the Barnard's Loop, and it surrounds the Orion Nebula. And the Orion Nebula is the upper right of the two spots inside of that C-like structure. So and there's massive structures that are off to the left, which is, I believe, the Rho-Fucus complex, and other structures that delineate star-forming regions. We can even see the Large Magellanic Cloud off the Milky Way down to the lower right, a lower portion to the right, about halfway out, and some other things that are very high up as well. In any event, that is H alpha is a result of star-forming regions and hot ionized gas, and this is, of course, from Finkbeiner, whose work with large numbers of surveys of the H alpha. There's three different sets that we're talking about: WHAM, VTSS, and SHASSA, which were massive H alpha surveys from the ground. All right, this is another view of that, just looking at the center of the image. And it's kind of spread out, so we're only looking at the key critical things, and it's a slightly different view. Instead of an ATOF projection, it's a projection that shows just the dominant events in the Milky Way. Centered again on the center of the Milky Way, we see a bright spot. So there is some star forming that does occur, but in general, most of the star forming is not towards the center of the Milky Way, which is another interesting discovery. All right, so the next thing we'll do is that there's dust, but we saw originally in the optical view that there was gas too. Well, there's not just gas, but dust. And so if we look at longer wavelengths of light, meaning micron wavelengths, which are 1,000 times longer than nanometers. So we're looking at, this was done by the Wide Field Infrared Survey Explorer, the WISE telescope, one of NASA's major space-based observatories, and it looked in numerous infrared bands. And what we see going across there is that we see a tight band that goes across the middle that forms the plane of the Milky Way with a strong amount of brightness towards the center. The colors are specific to infrared light, so this is a false color image, just like the H alpha was also a false color image because it's only one wavelength of light. The false H alpha is only one wavelength of light. So what we have here in this image is just simply variations of brightness. So red here is very, very bright, blue is very cool. Well, cool meaning not much light is coming there. So we say it's dim. So blue is where it's dim, red is where it's bright. And that's only in one wavelength of light. However, if we then go forward and look at this infrared image, we actually have composed it out of three different wavelength bands. So we can approximate each by a color. So the blue-green or the cyan is stars and galaxies. And so those would be starlight in general. The deep green will be dust and gas, will be mostly dust. So the green and red will be dusty emissions. So we can see that the blue, which goes in the center, since that's starlight or galaxy light, that's very tightly confined into the disk of the Milky Way. But the green actually has a puffy structure, and that puffy structure arises because, again, dust is associated with star-forming regions, and unlike the optical image, the infrared image of the blue that shows the starlight is not impeded by the dust, so it travels through the dust, and we could see the light of the collected stars in the infrared image. It also shows us that when we look towards the center of the Milky Way, we see most of the stars. And you can also still see the bulge at the center, which is a halo of stars, but the brightness of stars is pretty much confined to the disk in general. So the green shows where the dust is, and that corresponds to star-forming regions again. So dust here means particles that are warm, that are about the same size as cigarette smoke dust. So they're extraordinarily tiny objects, and they're many thousands of molecules in size. And so they're really kind of small objects. That's what we mean by dust. And the dust is not much bigger than cigarette smoke. All right, so let's look at longer wavelengths still, and this is in microwave wavelengths, and these wavelengths will be on the order of millimeters to centimeters, whereas infrared is on order of microns, which is a million times, which is 1,000 times smaller than a millimeter. Now we're looking in millimeter and centimeter wavelengths, and this is microwave region, and this is a map that's made by the European Space Agency's Planck telescope. And the Planck telescope its goal is to search primarily for the cosmic microwave background, which you can see above at the upper left and the lower right. But it also detects very strongly the Milky Way. So the Milky Way itself has huge emission in microwaves, and that comes from the dust and gas, mostly the dust, and also the galactic magnetic field actually causes the emission of this as well. So mapping the galaxy's emission in microwaves is extremely critical to understanding the cosmic microwave background, because the galaxy emits a huge amount of microwaves. So in any event, we see again the galactic center and the galactic disk going across. We see these huge cirrus-type clouds which go above and below, and they're very loosely surrounding the star-forming regions. Though whatever is emitting the microwave emission is usually it will be associated with dust and gas. It's extremely cooled processes, and so these will be this emission comes from essentially gas and dust again, which is very cold, and being influenced by the magnetic field of the Milky Way. All right, so let's then take it even longer, one of the more longer wavelengths of light in terms of radio. So microwaves get into the short end of radio frequencies. Now we're going into the full radio frequency, which is 21 centimeters, or about the length of a piece of paper, or the width of a piece of paper. And 21 centimeters is the wavelength that neutral hydrogen, or a hydrogen that is not in molecular form like two hydrogen atoms together, but a single hydrogen atom. And what's happening is that across the Milky Way, occasionally the electron in its orbit flips from being spin up to spin down, and it's an extremely low energy emission. And this very low energy emission is in the wavelength of 21 centimeters. So this map, where again, well now here, because it's at a single wavelength, we're again looking at the blue would be where it's not very bright, and the red is where it's very bright. And so it goes from blue all the way to red to show dim to bright. And so in the plane of the Milky Way, we see that the neutral hydrogen is strongly confined to the plane of the Milky Way. But we do see those cirrus clouds above and below, just like we see in the microwaves. So there is some, even though so what we see in microwaves is additional wavelengths of light that are being emitted by clouds of gas that also emit in radio frequencies, such as carbon monoxide, methane, and other simple molecules. But the neutral hydrogen is really the thing, because that's the thing that says stars are formed out of hydrogen, so this is a big thing. This was done over a very long period of time using the Parkes radio telescope, which is part of the Australian government, and so there's the key there, and this has been put together by and is held by the Lambda at Goddard Space Flight Center with NASA. So this is a full sky image again of the neutral hydrogen, and we see it's confined to the Milky Way, but we see two bright spots down to the lower right, below and to the right. Those are the large and small Magellanic Clouds, which are neighboring galaxies or orbiting galaxies of the Milky Way, and there's active star forming region going on in both. So neutral hydrogen is where it's happening. Now if we go even longer, almost instead of 21 centimeters, but 3 times longer, almost meter-long wavelengths of light, the Max Planck Institute at this particular wavelength of light, 400 megahertz. Now we're always talking the wavelengths we talk about FM and AM transmission. We talk about the so and so megahertz on your FM dial and so forth. But this is a 73 centimeter wavelength map of the Milky Way, and it's less and less resolved, because the longer the wavelength, the larger the aperture you need in order to resolve it. So the resolution is getting poorer as we go to longer wavelengths. But we can see again still that high cirrus cloud that seems to be coming up from the center of the Milky Way. But there's also lots of radio emission, and again, this radio emission will be due to cold, gas clouds, and the gas will be tracers of things like of molecular clouds. And so we have these cirrus molecular clouds that they're infused with hydrogen, but mostly towards the center. And the radio emission from the center is dominantly due to the magnetic interaction that the center of the Milky Way has on its surroundings. We can even go longer wavelength, and this is almost 10-meter wavelength. This is extremely recent data. This is from the previous data comes from the the All-Sky survey. This comes from the Planck Institute, and it was done a long time ago. And this has been cited many hundreds of times as a full survey of radio emission in the galaxy. So please check out that info. It also appears in the Lambda organization as well as the link below. But this one is from the LWA1, which is a low-frequency sky survey. And what's interesting about this is that this wavelength of light has never really been explored before. So when we look, and this is now a slightly different view, it's based out of New Mexico, and so they can't actually get a full sky image because there's only one array, and it's in New Mexico, so they lose much of the southern sky. And so here, instead of it being a galactic map, it's now an equatorial map. And what we see is that the galactic center or the galaxy is actually this kind of hoop-like ring that goes across. And this is their map, so I'm not going to spend the 20 hours that it would take in order to reframe this image into a galactic map. It would be kind of painful. But what we do see is that the loop, which is the Milky Way, the bright spot of the loop on the right is the center of the Milky Way, and we see some other really bright spots. So this survey of extraordinarily low frequency, which would be, who knows, like vibrational frequencies or rotational frequencies of large molecules in the Milky Way. But you can see that cirrus sort of cloud that's on the right-hand side, and possibly even what might be bright spots that might be associated with star-forming regions. In any event, you can go to their website, which is the LWA1, in order to learn what this science is. And this is a fully operational telescope, and they actually broadcast everything every 30 minutes. So it's kind of funny. It's really low energy and low power, so they've decided to kind of make a radio transmission of low frequency observations of the sky. And you can see Jupiter going across their live transmissions, as well as you can see the sun. You can see the sky moving. It's kind of cool. So it's very interesting full sky images of radio transmission being broadcast to you from New Mexico. So go take a look at it. Anyway, let's go to the other end of the side. So we looked at the very, very, very longest wavelengths of light. Now let's look at the shorter wavelengths of light. And here on the right, we see the X-ray emission that was seen by the ROSAT satellite. And so the ROSAT satellite looks in X-rays. And so instead of measuring this energy, the wavelengths in, say, nanometers or something like that, we're measuring in wavelengths that are so small that we might as well use the energy of the photon, and that's what they do. And that's why they said these three bands, which is the red is 0.25 kiloelectron volt, green is 3/4 kiloelectron volt, and blue is 1.5 kiloelectron volt. And why they do that is because that's the nature of the detector. The detectors really can receive or detect energies of X-rays. So that it's basically the detectors are different. And since the detectors are different, they quote their wavelengths different. In radio, we tend to talk about frequency. In visual and infrared, we talk about wavelength. But when we get to higher energy wavelengths of light, we just describe the photon energy itself. So it's kind of funny. We can look at this. We'll look at all that in some other things too. But the electromagnetic spectrum is their equivalent things. You can certainly do this, but it's more convenient to say 1/4 kiloelectron volt than say a sub-angstrom level wavelengths. So what we see here is we see the band. Now we're back to a galactic map. And we see a bright spot in X-rays off to the right. That's probably a pulsar. I believe that might be the Geminga pulsar. But we see the X-ray emission from that bubble, which appears to be over the center of the Milky Way. We have other bright spots of X-ray emission. But here, instead of it being red means hot or bright and blue means cool or less, here if you have a color, you have something. So black is simply where you don't have data. So dim or black is where there is no data. So it's fascinating to think that the higher energy wavelengths of light seem to be coming from the Milky Way band itself, and the lower energies are diffuse from the background of light that comes from outside. And so that diffuse X-ray emission, that red diffuse X-ray emission, is mostly extragalactic. It comes from the diffuse background of galaxies in galaxy clusters and center that are extraordinarily distant. But we look at the higher energy light energy X-ray emission, and that comes from the center of the Milky Way and along the plane of the Milky Way, and that probably is from pulsars and black holes. So let's go even higher energy into gamma rays, and gamma rays are being observed by the Fermi Gamma Ray Telescope, which was formerly known as GLAST, G-L-A-S-T, but they renamed it to the Fermi Gamma Ray Telescope. And this is an all-sky view of approximately, I think this is a 5-year data set. And so taking 5 years worth of data from gamma rays. And this particular thing, again now, because gamma rays are so difficult to detect, they would rather, this is where blue is, the darker the blue, the less the emission, the brighter the red, the more the emission. So here we see the Milky Way center is extraordinarily bright. The Vela pulsar, which seems to be the thing that we've seen left and right throughout here, that's a pulsar emitting strongly in gamma rays. The Geminga pulsar, which is only visible in gamma rays. The Crab nebula, which is visible in gamma rays. And then you've got this funny thing is blazar, and that is looking down the barrel of a jet, of an ultra-relativistic jet coming out of a supermassive black hole some billions of light years away. So one of the brightest sources in the gamma ray view of the sky is something that's billions of light years away. We're looking straight down the center of the axis of a supermassive black hole that's spinning and materials falling into it, emitting gamma rays, and we're seeing it billions of light years away. But the Vela pulsar is fascinating because it's bright in many wavelength regions, and it's a nearby pulsar that was formed maybe about 3,000 years ago, or maybe 10,000 years ago, in a supernova explosion. So these pulsars, these recent pulsars, like the Crab, Geminga, and Vela, are things that are a result of recent supernovae. The Milky Way center, though, that emission comes as a result of the dominant, brightest spot in the center of the Milky Way. There's actually a supermassive black hole there, too. So when we look at gamma rays, we're looking at either the emission due to extraordinarily hot processes on the surfaces of pulsars, or material getting to become millions of degrees in temperature and falling into a black hole. And gamma rays can also be bursty. And the gamma ray telescope this gamma ray telescope is showing the sum of all of it, but one of its main missions is to look for bursts, meaning some things that last for seconds only. And those are gamma ray bursts which herald the death of stars. So some of the tiny, tiny, tiny singleton spots throughout this map that are dim and blue are as a result of simply gamma ray emission from gamma ray bursts. And those tend to be distributed equally across the sky, and those are from the supernovae of ancient stars that may have exploded billions of years ago, and the light finally arrived to us in a very short burst of only a few photons. So what do we get? So astronomy can be done in many wavelengths across all the sky, and they're radio, infrared, visible, ultraviolet, X-ray, and gamma ray. We didn't really look too much at the ultraviolet sky, but that's with the GALEX observatory probe, and it's really, they have a very small aperture, so it's harder to make a full sky map with that. But radio light penetrates dusty regions. It can be used to study magnetic fields, interstellar clouds of gas and dust. The good thing about radio is you can make it just like the guys in New Mexico with their ultra-long wavelength. They don't care if it's cloudy or rainy, just so long as cows don't come in the pasture and kick over the arrays. So they've got some really big cattle fences around it. Infrared, you need to be in space to get full sky surveys, like the WISE spacecraft or the Spitzer spacecraft, because the Earth's atmosphere absorbs that. Visible light, we can put telescopes anywhere, and we can put them up in space, and that'll help us to make maps of the sky, and we get to see stars, the structure of the universe, and light from gas clouds. Ultraviolet light it must be from space as well, and that comes from extraordinarily hot stars, young hot stars like O and B type stars, as well as hot gas clouds. And X-rays come from neutron stars and black holes and active galactic nuclei, and gamma ray observing is from extraordinarily violent processes on the surfaces of neutron stars, as well as active galactic nuclei and hypernovae and supernovae. One of the most interesting things that is coming up online soon is the Large Synoptic Survey Telescope, or LSST. So I invite you to go look at that. It's currently under construction and should be done within a year or so. And its goal is to take hundreds of panoramic images across the night sky every night. And so the camera that they're building is one of the largest cameras, and they'll have so much data that it'll be impossible to study by an individual. So they're part of the LSST's mission is to get the data out into massive online capacity so that people can look at it. So basically it's a 6.7 diameter primary mirror, but there's a big chunk that's taken out of it for the secondary, because the secondary has to reflect to one of the largest cameras that's ever being built for an observatory. The goal is to be able to do things that are extraordinarily faint and be able to detect changes of position and brightness. So they're going to discover lots of variable stars, lots of comets, lots of asteroids, deep things in the outer solar system, things past Pluto, and see what the Oort cloud might look like. But it'll also be able to show changes in local nearby stars. And all of the exposures will be done over 30 seconds a pop. And so this camera, this 3.2 billion pixel camera, is going to record the entire visible sky twice each week. So this is going to be an enormous undertaking, and their public outreach is incredibly important because they want you to go look at it. So this will be one of the greatest observatories when it gets built on the ground, because its goal is to get the data to people. It'll transform the nature of optical astronomy in about a decade or so, and that's its goal. So I invite you to go take a look at all of this stuff, and I'll put all the links for all of the things that we looked at on the YouTube channel. So keep on looking up in the sky. See you soon.